let's see, where could it be? Looks like somebody liked it and they took it. Or maybe did I take it? I know I have hidden one up there. So we are looking at reliability analysis. Before reliability analysis, we have seen a little bit of probability theory. Kind of, some of that was sort of review. And so basically we want to define some reliability measures, and we have defined reliability. So unless we say qualify it, this is the measure of reliability, that it is the probability that unit operates correctly between Z to T during this complete duration. And there is availability, which is defined as the probability that a unit is operating correctly at time t. And then I was mentioning about transaction reliability. Which is the probability that a single transaction will be executed correctly. And then some of the other measures are mean time to failure. So, so this is the expected time the unit will work without a failure. And somewhat related is MTBF. And last time we saw that MTBF is actually equal to MTTF plus mean time to repair. And we saw one expression for MTTF, which is a rather useful one, and it says that you can get MTTF if you know the reliability and you integrate the expression for reliability between 0 to t. As I was mentioning, this is one of the results that is worth remembering. And then we were looking at a couple of special cases. Oh, incidentally, I also mentioned that sometimes we talk about a steady state availability, and that has something to do, we can express that in terms of MTTF and MTTR. And we talked about mission time. So mission time is the time it takes such that mission time is, let's call it, I'm calling mission time equal to, what is it that I'm calling mission time? M.
TM.
Mission time is basically, the reliability at mission time is equal to the threshold reliability.
Is it greater or equal?
Or you can say that it is equal, less than or equal to, but since reliability
Has to be greater or equal.
reliability should be, oh, sorry about that,
Yeah, greater or equal.
other way. I think this is what I had said. So as long as the reliability stays above the threshold reliability, you are within the mission time. Of course, since the reliability generally declines monotonically, so they will intersect when they are equal. So you could put equal there also. And we were looking at two specific cases. So these are the basic cases. Single unit with permanent failures. Single unit which eventually has a permanent failure, and other is a single unit with a temporary failure. Actually, you can have a combination of the two. We will talk about that next time. And I was mentioning about the bathtub failure rate. Failure rate. Now, failure rate is another measure of reliability. And I was mentioning that we will generally assume constant failure rate, and that is related with the observation, or I suppose you could say claim, that during the operational period of some unit, the failure rate would remain constant. It's a reasonable assumption in some cases. And if you want more accuracy, there are methods that are available that you can use. And one case we had seen for single unit with permanent failure, we had seen this. This is state 0 and this is a good state. And we have seen that P0 T, so we got a differential equation for this. We solved the differential equation and we obtained a solution, and we applied the initial condition, and we assume that initially the system is here, and a result of that we get that equal to minus lambda t, and hence reliability is equal to e raised to minus lambda t. Another result was remembering. So that's what we did last time. And let us, now today we want to save some time to maybe look at a couple of questions from the feedback module. But let us look at our single unit cases. Okay, so let us come back to single unit with permanent failures. So this is the case. And okay, so we got this. Now let us evaluate its, what about, this is the reliability. What about its availability? What can we say about the availability? Now notice that the fault is permanent. So if it is working correctly, it has been working correctly from time 0 to t. That means it is working correctly at time t. So availability is basically same as reliability in this case. In this case, there is no difference between availability and reliability.
Can you say why again, please? Why?
Pardon me?
Why do we consider it the same as this?
Because definition of availability is that probability that it is working correctly at time t.
Yes.
Definition of RT is probability that it has been working correctly from 0 to t.
Okay, right. Yeah.
And since the failure is permanent, so if it is working correctly at time t, that is the same thing as the probability that it has been working correctly since time 0 to t.
Right.
Because if since the failure is not temporary,
Mhm.
so they are same. But if it was temporary, that would be a different thing.
Right.
So yeah, that's a good question, and we will come back to this when we look at the single unit with permanent failures, I'm sorry, temporary failures. Okay, now let's do MTTF. Okay, so let's come here. So this was a quick review of what we were doing last time. Now there are a couple of ways you could possibly approach this. One convenient way would be since we have the expression for RT, why don't we just plug it in our formula. Okay, how many of you remember integration? Well, I guess if you're an engineer, you probably do it every day. I guess even a computer scientist, depending on specific things, they don't need it that often, but it comes up depending on, I guess, your line of research. So there are, now I had studied a lot of stuff when I studied integral calculus, and I don't know if I remember everything now, but there are a couple of basic things that you should remember. And one of them is the fact that, okay, so I substitute for RT, and that is e raised to minus lambda t dt. Now this is something that you should remember. Integral of e raised to minus x dx is equal to just e raised to minus x. And now, of course, in this case we have lambda, so we are going to get this equal to e raised to minus lambda t, but it needs to be divided by minus lambda. And of course, we take the limits 0 to infinity, and e raised to minus lambda t infinity is 0. So we are left with, so we get MTTF equal to 1 by lambda. So for a single unit with permanent failures, if the reliability is given by this, which is the typical assumption, then MTTF is inverse of the failure rate. And that actually was one of the things that we had said in anticipation, even before we had seen much of the theory. Okay, let's look at an example and put in some numbers. Now I have found that in any kind of theory, sometimes you can build a nice theory or some mathematics, but unless you plug in some numbers and make sure that the answers look reasonable, you cannot be confident that your mathematics is right. And even if the numbers are simplified, or even if they are kind of just some assumptions. Okay, here's one example. Let us say a unit has MTTF equal to 13,000 hours, and find failure rate. And of course, in this case, failure rate is 1 by this. And now keep in mind that with simple calculation, it is you're very likely to make mistakes. So just because this is a simple calculation, and obviously you will see that this is equal to 1 divided by 3 multiplied by 10 raised to minus 1, 2, 3, 4. And so that is equal